Okay, so let's get started. Hi, everyone. Welcome to COMS 6998. This is a topics course. It's on the frontiers of quantum complexity and cryptography. And all the course information will all be on that link that's shown on the screen. So it's on my homepage. You can just Google my name and find it. And everything will sort of be channeled through there. So I won't really use CourseWorks except for maybe an occasional class announcement or something. Yeah, so you can get the information there. So what's this class about? This is going to be a research level course. Okay, so it's sort of focused on like cutting edge research topics. And the theme of this particular course is on something called the complexity of quantum states and state transformations. And this is a subject that, okay, so picking up where I last left off, this is a topic that's sort of just emerging, and we're going to be exploring the different things that people have worked on recently in this area, but it's really kind of like not a well-formed research area, but it's very, very interesting, and I hope to convince you of that in the next few minutes. I should say that this is going to be a pretty theory-based, math-based course. Okay, so there's no like programming involved. There's no it's all theoretical. So just so you know what to expect. Okay, so for the next like half hour or so, I'm going to just give like a very broad overview of like where this theme comes from, why I think it's interesting. And after that, I'll go over some like course details, like administrative stuff. And then we'll take like a 5-minute break. And then in the second half, I'll give like a very quick and brief review of quantum information. Okay. All right, so I'm just going to zoom out a little bit and sort of like situate where we are in terms of this whole area of like quantum computing and quantum information. So let me draw a timeline, like a very, very zoomed out timeline of what's going on in quantum computing. All right, so here's today. All right, and most people will pinpoint 1982 as kind of like the genesis year of the idea of quantum computing. There's some stuff that goes on before that I'll mention in a second that actually occurs in the late 1960s, which is some kind of like prehistory. And I'll say something about it momentarily. But quantum computing really started in 1982. People came up with the idea that, hey, maybe we can build a different kind of computer that's based on different principles. This is attributed usually to the people like Feynman and Deutsch, Benioff, a few other people. And they had this idea, and everyone sort of just ignored them. It's kind of like this crazy idea. There's another development just a few years later in 1984, which wasn't about quantum computing per se, but people came up with the idea of quantum key distribution. So this is when this idea that you could use quantum information to perform cryptographic tasks that you couldn't do classically, this is when that idea was born. So Charlie Bennett and Gilles Broussard came up with this protocol that allows two people to use quantum equipment, transmits quantum states back and forth with each other, and they can use that to generate a secure key between themselves, right? And using that key, you can do all sorts of like secret communications and so on. And the amazing thing about this is the security of this protocol only depends on the laws of physics. It doesn't depend on the hardness of any, assuming that factoring is hard or some other computational problem is hard. So that was kind of notable. The interesting thing is, and this is where the prehistory comes in, is that the idea for quantum key distribution is linked to some work that someone named Steve Wiesner came up with in the late 1960s. And the story about Steve Wiesner is that he was a physics graduate student at Columbia. And he had this idea of like, maybe you can use quantum states to do information processing. And that was like a totally radical idea. He came up with this idea, he like wrote up a paper, and as often as like many of these stories go, he like submitted the paper to places and no one appreciated the significance of this. He came up with this idea of something called quantum money. It was this idea that you could use quantum states to represent money. But the property about this money is that it's physically unclonable, so you can't make copies of it. So it's a type of money where you can't counterfeit. And the reason you can't counterfeit is because of something called the no cloning theorem in quantum information. And this was like so ahead of its time. And he wrote this paper, like no one appreciated it, and he quickly left academia. But he told this idea to Charlie Bennett and Gilles Broussard, and actually the same ideas that went into quantum money led them to think of quantum key distribution. So that's kind of the connection. Okay, so 1982, 1984, then come the 1990s, and still like quantum computing is this really curious thing that no one really cared about. But of course, there was this big splash in 1994 when Shor's algorithm came out. All right, and this is the famous factoring algorithm, shows that you can factor large integers efficiently on a quantum computer. And that was really sort of provided the impetus for lots of people to care, especially because if you can build a quantum computer and run Shor's algorithm, you can break the security of RSA, right? So that obviously makes people stand up and pay attention. And it gives you evidence that actually quantum computers are not this obscure exotic thing, but you can use it to solve problems that people care about in ways that are far more efficient than we think classical computers are capable of. And then, of course, starting from then, it really led to lots of interest. 1996, there's Grover's algorithm. Maybe I should use a smaller font. Grover's search algorithm. Okay, right. This is an algorithm for doing unordered search. Right, you can, given a list of n items, you can locate a desired item with only square root n queries to the list, right, using a quantum computer. I'm not going to go through all the milestones, but this one is particularly significant. In 1998, there is a result called the fault tolerance theorem. And what it says is, actually, it's possible to build a quantum computer in a noisy environment. And if you had, if you can correct errors that are occurring on this computer fast enough, then you can actually ensure that the computer will run the computation flawlessly and you can solve the problems that you're interested in, right? Because before this fault tolerance theorem came out, people said, well, it's really nice that you could, have Shor's algorithm and Grover's algorithm, but you can never implement it, right? Quantum mechanics is way too fragile. Quantum states are way too fragile. Like if you try to build a quantum computer, it would inevitably fail. So it's just not practical or relevant. But this fault tolerance theorem says, actually, you can build it. And this really launched, the remaining, till today, this sort of gives the reason for people to try to build quantum computers. And it says that it's actually a practical thing to do. Okay, and then, since 1998, from then on, like lots of really cool stuff happened. I'm not doing all of the history justice, but there's just lots of research. And here we are today. And like it's really different. Like, of course, everyone's heard of quantum computing now. There are many companies that are trying to build quantum computers. There are, in fact, as of today, 2 publicly traded quantum computing companies, which is like hard to believe. Like, and I'm not talking about like Google or IBM, but like these are companies whose sole mission is to try to build quantum computers. So it's quite a different world today. So that's the that's the story. And why am I mentioning this? Well, because I want to say, like, in some sense, part of the reason that people are so motivated to build a quantum computer is this belief that quantum computers can solve some problems much, much faster than any classical computer can. And what's the basis for this belief? And it's the basis is quantum complexity theory. Right. Like, why do we believe that there's some problems you can solve more efficiently on a quantum computer than with a classical computer? The theory to explain that is supposed to be quantum complexity theory. And if we don't have a good understanding of that, then in some sense, like this whole quest, this whole journey to build a quantum machine is not really on good scientific grounds, right? So it's very, very important that we really understand this theory, right? What makes a problem amenable to be solved on a quantum computer? When is it faster than, when can you solve it faster than classically? Right? So, so this is a really, really important thing to understand. So what is quantum complexity theory? Well, complexity theory in general, it's the study of computational resources that you need to solve different problems, right? Probably most of you have heard of, P versus NP and things like that. That's all complexity theory. The goal of quantum complexity theory is, well, you want to understand the difficulty of solving computational problems with quantum resources, like using a quantum computer, as compared to using classical resources, right? And like I mentioned, the most important question in QCT is, are quantum computers more powerful than classical computers? And as important as this is, it's still an open question. We actually don't have any complete proof or complete argument saying that quantum computers are more powerful, right? For all we know, tomorrow someone might wake up and have a brilliant idea for a classical algorithm to efficiently solve quantum computations, in which case all of this quest to build a quantum computer, in some sense, it's kind of pointless, right? Maybe not completely, but essentially like a large motivation would be gone. So, this is still open, right? And this kind of like necessarily so, like definitively separating the power of quantum versus classical computation would be on the same level as, essentially speaking, as like separating P versus NP. Like it's that kind of thing. So it's a very, very difficult mathematical problem. As far as I can tell, we're nowhere close to actually proving this outright. But there's still been like a lot of wonderful progress in this subject. We've learned a lot. And what are some of the things that people have studied? So people have said, well, we can't prove outright that quantum is better than classical, but maybe we can try to understand the differences between the two in restricted models of computation, right? Where you place constraints or you consider special models of computation. So for example, a very important model is something called query complexity. Okay, I won't really go into what that is, but it's kind of a model where you assume that your computational device gets access to the input in some black box manner. And in one case, you have quantum access. In one case, you have classical access. And there we can actually prove using quantum access, you can solve problems more quickly. Right? It's not the most general kind of computational model, but it's like a very natural one. And it gives us a lot of insight into how quantum could give us an advantage. Okay, so that's one. Another is communication complexity. So here you're thinking about distributed computations, right? Like you have, let's say Alice and Bob, these two parties, they both have their own inputs and they want to compute some function of their inputs. And let's say they're allowed to transmit qubits between each other, right? Rather than bits. And there we can prove qubits actually help you compute some functions using much fewer communication than classical bits. Right? So there's lots of cool results there. There's been a lot of work in exploring quantum analogs of these complexity classes that you've probably learned in like a computer science class. So, in the classical world, you've probably heard of these complexity classes like P, stands for polynomial time, all the problems you can solve efficiently on a classical computer. There's like NP, right? That contains like 3SAT and traveling salesman. Here's I'm just going to write some classes. Here's P space. There's another class called MIP and so on. There's like, there's a whole zoo of complexity classes that people have come up with corresponding to different models of computation and different computational power. And in quantum complexity theory, people have looked at the analogs of this. So the quantum analog of P is BQP, okay. Bounded error quantum polynomial time. So it's all the problems that you can solve on a quantum computer in polynomial time. There is a quantum analog of NP. It's called QMA. Maybe we'll talk about that in this class. There's quantum polynomial space. And there's a MIP star is a quantum analog of MIP and so on. So, complexity theorists have come up with all these analogs and they've kind of tried to understand, well, first, how do all these classes in the quantum world relate to each other, right? Do they satisfy the same relationships as the classical classes do? And again, really importantly, how do these two worlds compare, right? Like, does BQP contain NP, right? That was a really important, interesting question. It's still open, we don't know, but we don't think it does. In other words, we don't think quantum computers can solve NP-complete problems efficiently, okay? Things like that. So there's been all sorts of theory and all sorts of results that people studied. It's all very nice. But here's the thing. So all of this theory that people have studied, in some sense, it's all just really quite attached to its classical complexity theory roots. It's all focused on computational tasks with classical inputs and classical outputs, right? So for those of you who've taken complexity theory, right, you might remember that a complexity class is really a class of decision languages, right? So, right, what's a decision language, right? It's a decision problem. It's a problem where, you get in some input, right? Like maybe you get as input a graph. So you get in a classical input. You get some graph G, and you want to know, is it, I don't know, does this graph have a Hamiltonian cycle? Or is it planar or something? And the output of this task is to determine yes or no. So you get a classical output. All right, so that's what I mean by a task with classical inputs and outputs. And it kind of makes sense, right? Like, first of all, a lot of the people who are working in this area, they were trained in, say, classical complexity theory, right? So we want to bring all our intuitions and all our frameworks for studying the difficulty of computational problems. And traditionally, you only talk about problems with classical inputs and classical outputs, right? You also want to do this because you want to compare like classical versus quantum computing. So it kind of makes sense to put them on to talk about the same thing, right? So you want to compare like complexity classes with each other, and they all have to sort of refer to the same thing. So in this case, people talk about decision problems. All right. But now that we're sort of like entering this realm where people are trying to build quantum computers, at some point we're going to expect people to routinely transmit quantum information to and from each other. Maybe they're performing some quantum cryptographic task. Maybe they're running some like really sophisticated quantum physics experiment or something. And there, like this whole framework of classical input and classical output doesn't make sense anymore, right? It doesn't naturally capture the type of stuff you would do in a world where everyone has a quantum computer, right? And there are many natural tasks that that I'm going to describe to you that aren't captured by this standard framework, right? So so here's an example. Like, let's take an example from quantum physics. Right? Like, what's a natural thing that a quantum physicist would do? I'm not a quantum physicist, but this is like what I imagine what a natural thing they would do. They have some lab equipment, right? And they have some input, which is maybe some exotic materials or some like exotic physical state that they are able to prepare, or maybe someone handed to them. Right? And they want to learn more about it, like what are its physical properties? So they want to, say, extract some numerical estimates of a physical property of interest. All right, that's what quantum physicists do for a living. And clearly the input to this task is a quantum state. It's not a classical string, right? The output is still classical, but the input's not. Right, so that's like a very natural class of things that people do that it's falls outside of the traditional framework. Here's another thing that a quantum physicist might try to do. Maybe they get a classical input this time. They get down some description of some really interesting physical system. So they get a classical description of a physical system. Okay. What does that mean? Well, like in physics language, maybe this is a description of a Hamiltonian. Okay, this is sort of, in some sense, like a description of the laws of this physical system you're interested in. You get this as input, and the output is you need to prepare the lowest energy physical state of the system. Right, and which in general is a quantum state. Right, so here you have a quantum output. Okay, so that's one example. Just in terms of like two more examples, a very natural one is quantum error correction. Right. What task is this? Well, you're running a quantum computer, and there's going to be noise for sure. So whatever computation you're running, there's going to be noise that's affecting it. So you want to clean up the noise. So here as input, you get a noisy quantum state. and you want to do some sort of quantum process to clean it up. And you want to get say clean quantum state. Right. So here's a very natural task, very important one. And it has quantum input and quantum output. One final example, this one may be inspired by quantum cryptography. So I mentioned this BB84 protocol for quantum key distribution. This is a protocol where Alice and Bob, they're going to use quantum equipment to send these quantum states back and forth to each other. And I said it's secure, and what does that mean? Well, it means that, let's say there is an adversary that's intercepting their communication. So this adversary is like listening to the quantum channel between Alice and Bob and sort of scooping up all the qubits that are being sent across. The adversary is looking at these qubits and trying to figure out what secret message or secret key are they trying to distill out, right? That's a task that the adversary wants to perform. This is the intercepted quantum communication. And let's say the adversary, I don't know, there's all sorts of things that maybe it wants to like tamper with it and kind of embed like, a weakness in it maybe. So maybe it outputs some kind of tampered quantum communication, or maybe it just wants to directly break it and trying to extract the secret key. This is another computational task. What we want to show is that it's infeasible for a quantum adversary to do this. Actually, in the case of BB84, it's impossible, but other cryptographic tasks, maybe we want to argue that the adversary can only do this if it spends exponential time, right? It can't do this in a reasonable amount of time. So hopefully like these examples kind of give you a sense that like, wow, these things are pretty natural. And but the kind of the striking thing is we don't really have a unified theory or language to understand these tasks and how they compare with each other, how difficult they are. So here are the questions that are really going to guide us in this course, and that we don't really have good answers yet, but I'm hoping we'll at least get to explore these questions and maybe, I don't know, maybe as part of your course projects, you'll come up with potential answers to them. So what are these questions? How do we prove upper and lower bounds on the complexity of these tasks? We have this huge, long studied theory of complexity theory. It's this beautiful, rich theory. We have all sorts of techniques, but not all of it applies to this quantum input, quantum output setting. So we'll definitely need to develop new techniques to study these problems. How do we organize these quantum tasks into different classes? Like, just like we have these complexity classes, P, NP, BQP, QMA, and so on, can we, I don't know, come up with some other classification or categorization of these quantum tasks? We don't have such a thing yet. Can we relate quantum tasks, like their complexity, to classical tasks, right? It'd be really nice if we can at least leverage somehow classical complexity theory, or in some cases, but maybe in other cases we cannot. And all of this, we're studying. I mean, it's intrinsically interesting on its own, but there are actually a lot of applications. So as we'll see later in the course, a lot of these questions come up naturally in physics and in cryptography, right? Like I just mentioned. And so they'll definitely have, in some, like, if we understand the complexity of these tasks, they'll tell us about things we can actually do in the lab, the security of different protocols, and so on. And finally, like, by studying all of this, it should give us a much deeper understanding of the nature of quantum information and what makes it so different from classical information. Okay, so before I move on, any questions or comments or? All right. Okay, if not, so I'll just give a very quick summary of like some of the things that we'll be talking about in this course in particular. All right, I just sort of gave you like the high level theme, but in terms of specific topics, what are we going to learn? There's going to be roughly 5 parts to the course. We'll spend a couple weeks each on each part. Today is, just a general introduction. We're going to go over some basics of quantum information because I'm not assuming everyone has taken quantum info before. And then the first part is we're going to look at ways that we can learn about quantum states, something called tomography. The second part is how do we synthesize them? How do we generate them on different kinds of quantum states? Like what's the complexity of doing so on a quantum computer? What's the complexity of synthesizing not just states, but what if you want to perform a transformation on them? We'll talk about quantum crypto. Depending on the time, hopefully we'll get to some interesting connections to physics. And then finally, the last part, which I think is the most important part of the course, are the course projects, which you guys will be doing. So you sort of explore a topic of interest that you're interested in. Okay, so maybe let me just give say a couple things about part 1, this part that's coming up starting next week. So learning quantum systems. What makes quantum systems, there's a lot of things that make quantum states so different from classical states or classical information. And one of the reasons is that in some sense, they're exponentially more complicated than the corresponding classical information, right? So if you have an n-bit string, like what's the amount of information that's contained in it? Well, it's like tautological, it's n bits. But if I give you n qubits, an n qubit quantum state, to write down a classical description of this state, you need to write down 2 to the n different numbers. Right? It's an exponentially large description, right? And that's kind of crazy, right? Like you have n qubits, maybe n is not even that large. Maybe it's like 80 qubits, but somehow to write down, like there's not enough not enough atoms in the universe to like write down every single degree of freedom of this 80 qubit state. So these states are really complicated, and this first question, or this first part on learning quantum systems, is like, suppose I gave you a quantum state that I've generated. What would it take for you to be able to extract this classical description? Right? And this is called tomography. Okay. And in general, this will take you exponential time to perform, but still, like, how do you even do it, even if I did give you exponential time? That's the first part, extracting a classical description of a quantum state. Okay, it's very resource intensive, but it's like very important to physicists today because this is how they verify like the state that they prepare in their lab is actually the state they wanted. So how do you actually do it? And there's been a lot of work on how do you perform tomography. There's been more recent developments saying, well, what if I wanted to get a classical description, but not the full 2 to the n size description, right? That's too large. I don't have that much time. But what if I wanted to get some classical description from which I can extract the information that I'm interested in, right? Like you can imagine a quantum experimentalist would say, I don't want to know all 2 to the n amplitudes of the state. I just want to know like, the expectation value of some measurement, right? That's what I'm really interested in. Or maybe like a small list of measurements. Is it possible to get some succinct classical description that allows me to do so? And that's the subject of shadow tomography. And this is like a very recent development. Like the kind of the amazing thing is it is possible to obtain these what are called classical shadows. Right? To estimate certain, we'll call them observables. I'll explain what that is later down the line. Like the, yeah, it's kind of amazing that it's possible, and it works in some cases and doesn't work in others. And it's like a very active research topic to try to figure out how can we make it practical and useful for what we want to do. So that'll be like the first part. Right, I mentioned synthesizing quantum systems. We'll talk about some quantum crypto. And hopefully, I would really like to be able to get to this connections to physics. A lot of this state complexity and these questions actually come out of investigations of this black hole information paradox, which is really cool. Okay, so what is this class not about? Right, so it's definitely not an introduction to quantum computing or quantum information. I mean, I'll have a very quick review of quantum information, but it's not going to do the whole subject justice. If you really like to get like a thorough course, I believe hopefully this semester there should be a introductory quantum course that's offered by Lior Horesh and John Smolin. And I think the information about that should come up shortly. So if you're interested in, if that's what you're interested in, you should keep your eye out for this course. You're not going to learn how to build a quantum computer. We're not going to see how to program a quantum computer. And there's no blockchain, even though there's crypto in the title of this course, in case you were confused. Okay, so that's the content of the course. Now let me sort of turn to the class admin stuff really quick. I'm going to switch over my share screen. Let's see. Where's the window? Okay, so if you go on the class homepage, and you go to the class page, there's a link to the syllabus, which is this Google Doc, and it'll have the course information, and let's just quickly go over it. So the first thing that's really important is there's a Slack channel that we'll have discussions on, and it's a place to ask questions and discuss with others, and also for us to sort of get to know each other. So you can just click the link there, and you'll be able to join. Right. Okay, so we went over what is this class about. So I should probably turn on notifications. Okay. Prerequisites. All right. So I know there's probably like a wide range of backgrounds in the people in this class. You don't necessarily have to have taken quantum computing before, but you must have at least taken some classes that have like significant mathematical content or are proof-based. So you should definitely be very, very comfortable with basic linear algebra and basic probability theory. So the math we're going to use is not very advanced, but like you have to be very comfortable with things like eigenvectors and projection matrices and linear independence, vector spaces, that kind of thing. Hopefully you should have either taken like an upward level computer science theory class, some quantum physics class, or quantum computing. And if you're unsure about your preparation, just reach out to me. Be more than happy to discuss. Yeah. And if you want to get a good sense of like at what level this course will be, if you look at this fall 2020 class link right there, you can sort of see the level of material that we'll cover. All right, so what are the assignments and how do the grades work? So it's pretty straightforward. There's a final project, that's the bulk of this course, that's 40%. There's gonna be approximately 3 problem sets. That'll be 30%. There'll be scribe notes. So we don't need scribe notes today, but starting next week, we'll have 2 people per lecture. One person will scribe 1 hour, the other person will scribe the other hour. And that'll be like a really useful resource for not just the class, but also people outside, like researchers who are interested in this area. And also 10% will be on participation. And how is participation measured? So generally speaking, it'll just be, hopefully you'll be interactive in class, like you'll ask questions, participating in discussions on the Slack channel. And also, every few weeks, I want to do something called a class discussion session. So basically, before each Q&A session, we'll have you guys submit either your questions or comments or interesting things, thoughts you've had, and then we'll sort of put them up on the screen and we'll just do a free form discussion and just see where it leads us. And basically it's our chance to see, figure out what you guys are interested in, interesting thoughts you might have, maybe connections to stuff you've studied elsewhere, and things like that. And so it's more of a free form kind of interaction. Okay, let's see. I mentioned scribe notes. Problem sets. Yeah, collaboration is definitely encouraged, but please limit the groups to size 3 or less. And everyone should, write their own solutions and so on. And we'll use Gradescope to, upload your assignments and so on. Final project. You can pair up if you want. And I'll have more information about this soon, but basically, I'll have like a list of topics that you can choose from. You can also pick a topic of your own. You just need to talk to me. And basically, you should just read like the papers in it, in that area, and sort of write a summary or project report. Oftentimes in the past, people have often also tried to do original research, and it's also and it's really cool to if you want to do that. So that should be it for the class admin stuff. Any questions about that?
I do have a question. Do you plan on offering a quantum computing course, either this one or a similar one next semester?
Not next semester. My vague plan is in spring 2023. So a year from now, I'll probably offer the intro quantum computing course.
Okay, thank you.
Yeah. Any other questions? Okay, so if not, then how about let's take a 5-minute break. So let's come back at 3:05, and then I'll for the remaining 50 minutes, I'll do a very fast review of quantum information. Recording. So the first problem set, which is going to be a math and quantum info review, is going to be released tonight. So that'll be on the class homepage, and it'll be due January 31st. And then we have a TA for this class. This is Hamoon Musavi, and he will hold office hours next week to help people with problem set 1. Just, as people are sort of either you've seen it before and you just want to get your feet underneath you, or maybe you're learning it for the first time, but you have other math background, and hopefully can pick it up quickly. But he will hold office hours. I'll also be available to help you with it. So it's just to make sure that you're comfortable with the math, the notation, and things like that. So the rest of the course is understandable. And like I mentioned, please join the Slack channel, and in the general channel, please introduce yourself, say who you are, your year, department, major, interests, things like that, just so we get a sense of who's in this class and what everyone's interested in. Okay, someone asked, Rosher, you asked, is it okay if you don't have any background in classical crypto? That's absolutely okay. So I'll basically, essentially everything I'll teach what you need to know as we go, right? Again, the only thing that you really need to know is just be very, very comfortable with linear algebra and probability theory. And you've either seen some quantum or like some complexity theory or algorithms or something like that. Okay. Cool. Any other questions about admin stuff before I jump into quantum info? All right, so this is going to be like an extremely light and fast review of quantum information. And it's going to go kind of fast, but the good thing is there's going to be lots of resources available to help you review it more carefully. So in particular, for example, the slides that I'm going to be using are borrowed from a 3-hour online crash course that I gave last year. And so it has all the same information. There are videos, there's annotated slides. If you go on my homepage again, under teaching in spring 2021, there's a link to this. You can click that and you can sort of check out all the stuff there. If you want an even more extensive review, I taught a whole semester class on this last year. And there's also videos and notes and stuff like that. So there's plenty of resources for you to look at if you ever need to brush up on this stuff. Okay. But here we're going to start from the beginning. We're just going to go over the basic postulates of quantum mechanics. We're going to go over this thing called Dirac notation. And then we're going to talk about composite quantum systems. So the starting point for quantum information theory is, you can think of it as it's a generalization of classical probability theory, where the probabilities can be negative or even complex numbers. Okay. That's the one sentence high level. So here's the perspective that you can start with. let's say that there's some physical system of interest, the system S, and the system can be in one of D distinguishable states, numbered, let's just number the states to give them labels, 0, 1 up to D minus 1. And there's some observer E that's external to the system, okay? Think of that observer as you, and you're trying to like assign a state to this system. I see a question. Okay, good. Okay. There's two things that can occur. Either the external observer E can measure the system S to get the state. When you measure it, you get a number between 0 and D minus 1. Or if you don't measure it, the system can undergo isolated evolution. If the system S can change, essentially it's changing because it's like, undergoing the laws of physics, or just doing its thing, right? And it undergoes this evolution without interacting with the external observer. So let's just talk about classical physics for now, because that's where our intuitions come from. Initially, this observer E is going to assign a state to the system. What's a state? Well, we can model it as a probability distribution over D states, right? So the state is just going to be this column vector, and it's going to be numbers that say what's the probability that the system S is in a certain state. So here, since we're talking classical probability theory, all the probabilities are non-negative, they sum to 1, right? But if the observer measures the system is going to be in a definite state, right? So it's going to get a state I, and it's going to get the state I with probability Si. And the state of the system now gets updated because the observer knows exactly what state it's in, right? And just to like use some kind of, like foreshadow what's next, we'll just say that the state has collapsed to this deterministic state of being in the state I. Okay, that was measurement, but what about this isolated evolution? Well, it gets up, it evolves according to a stochastic matrix. So initially the state was in some column vector S. And when the state gets updated, it has to be another probability distribution. And the things that describe how these things evolve are stochastic matrices. So you perform, you multiply the state by a matrix. That's a stochastic matrix. And the output of a stochastic matrix is going to be another probability vector. Okay. All right, so that's the classical setting. The extension to quantum is going to be kind of analogous, except instead of modeling the state of the system by a probability distribution, we model it as a complex unit vector. So the state of the system can, there's still D distinct states. So we have a column vector that's of length D, but now all the entries can be complex numbers. And what's the normalization? If you take the magnitude squared of all of these entries and sum them up, you get 1. So these entries, these alpha i's, they're no longer called probabilities, but they're called amplitudes. Okay, so that's what I mean when I originally said they can be negative, they can be complex numbers. So they're kind of like probabilities, but they behave in different ways. So we call them amplitudes. So that's how quantum states are represented. There are these unit vectors with complex entries. And, but there's D special states of the system, and they're called classical states, and they sort of coincide with the original classical states that we saw before. And these special states they're going to be these elementary basis vectors. Okay, and we're going to use this funny, bracket notation to denote quantum states. So whenever you see this bracket kind of thing, first, it means it's a column vector. And secondly, it means it's some kind of quantum state. So we have, bracket 0, bracket 1, d minus 1. And what they refer to are these specific quantum states. And, you can see that they're all orthogonal. And this is called the standard basis, right? Because it's the basis that you would normally use to describe this d-dimensional space. All right. So these are the classical states, but if you have a general quantum state, it's going to be a superposition of these classical basis states. Every quantum state, right? It was this column vector, but you can equivalently write it as this linear combination of the basis states, right? And these alpha i's are going to be, you can sort of think of it as like the probability of being in the state I, but it's not quite. Okay, it's the amplitude of that state. All right, so before I go on, let's just make sure we understand this Dirac notation really well, because we're going to be using it throughout the course. And it's notation that comes from physics, but it's just incredibly useful, I think, to just work with linear algebra in general. So again, whenever you see this bracket notation, we call it a ket vector. It just means it's a column vector of some sort. If you want to take the dual or something called the Hermitian conjugate of this column vector, you get a row vector. And these are called bra vectors. Okay, so let's say we had a two-dimensional column vector here. So we have ket psi. If you flip the brackets around, right, then this is called bra psi. And when you see the flipped brackets, it tells you it's a row vector. So it's a dual vector. And when you take the dual, you also have to take the complex conjugate of the entries. So that's why you have this A star, alpha star, beta star, right? They're the complex conjugates of alpha, beta, and it's a linear combination of these row vectors, bra 0 and bra 1, okay? So why do we use this notation? Well, it's really useful to quickly pick out what's a number, what's a vector, what's a matrix, what's a tensor, right? So for example, let's say we had a ket vector psi. It's two-dimensional, so it's a alpha 0 plus beta ket 1. Let's say we have a row vector bra theta. It's this linear combination of bra 0 and bra 1, right? So let's say we want to take their inner product. So we'll put the row vector next to the column vector. And you see this, you sort of have this bracket, and it tells you that what you should get out is a number. So you're going to take the inner product between these two vectors. So this is the same as gamma star, or sorry, not gamma star. Let me, it's gamma comma delta, right? It's a row vector. The reason there's no star is because we've just defined bra theta to be this linear combination. And we just stick in the column vector here. You do the inner product, you get alpha gamma plus delta beta. So that's the number you get out, the inner product between these two vectors. And the reason we call them bra and ket vectors is because when you put them together, you get bracket, right? So it's kind of a nice mnemonic. Another way that they're useful is you can quickly pick out outer products. So if we first put a column vector here, ket psi with bra theta, you don't get a number, but you get a matrix, right? So that's kind of like the situation when you put the column vector first and then the row vector, you do the multiplication and you get you get a 2x2 matrix. So that's what, these two things are the same. All right. So, here's another illustration of why this notation is useful. So let's say we had a matrix M, right, which is this outer product, and you want to apply this matrix to a vector, right? In this case, vector phi. So when you do the matrix vector multiplication, you just write one right after another, right? So this is the matrix M, this is the vector phi. But notice we can sort of snap these two together because here you have a bra vector and a ket vector. And you get this equation or this expression, which is like you've kind of written the same thing, but you put the space in a different place. But now notice that here you have a vector, a column vector, and here you have this inner product, right? So that's a number. But that's exactly what you were expecting, right? Matrix times a vector is a vector. That's what you got. All right. Good. And another way is that if you have a matrix with, let's say, entries Mij, okay, then you can equivalently write this matrix M as this linear combination of these outer products, right? What is I and J? I is just this column vector that's 0 everywhere except 1 in the ith coordinate. And J, bra J is this, row vector. So this outer product, ket I bra J, is just going to be a matrix that's all zeros except for 1 in the ijth entry. Okay. So hopefully that should be pretty intuitive and natural too. Okay, so if anything like this, if you haven't seen this before, this like getting used to this direct notation is probably the most important part of what you need to take away from this refresher. Okay, so let's go back to the quantum physics. We talked about how you represent states, right? You have these complex unit vectors, and then what are the two things that can happen? You can measure and it can undergo evolution. So how does the measurement work? So if the observer measures the system S, then you're going to get a classical outcome. So measurements of quantum states always return classical outcomes. You're going to get outcome I. It's a number between 0 and d minus 1. The probability that it occurs is going to be the magnitude squared of alpha I, right? So alpha I was its amplitude. That's not the probability, but if you take its absolute value and square it, it's a probability. And then the state of the system gets updated. It gets collapsed from the original state psi to the classical state I. And if you measure this system again, it's still going to be collapsed in the state I, unless you did something else to it. Okay. So that's the measurement rule. Okay, and what about evolution? You also evolve it by multiplying the state by matrix. It's not going to be a stochastic matrix, but it's now going to be what's called a unitary matrix. Okay. What's a unitary matrix? It's a D by D complex matrix whose inverse is the same as its Hermitian conjugate. So U dagger. U dagger, it's if you take the transpose of the matrix and you take the complex conjugate of every entry, right? So basically what's described in this quantity here. So the key property of unitary matrices is that if you apply a unitary matrix to a quantum state, you get another quantum state out. It's going to be another complex unit vector. Okay. There's a bunch of equivalent definitions of a unitary matrix. The first one is what I said. The inverse of the matrix is the same as just transposing it and taking its conjugate. That's equivalent to saying it maps unit vectors to unit vectors. And also, unitary matrices preserve inner products between vectors. So what does that mean? It means, let's say you have two vectors, let's say psi and theta. Psi and theta have some inner product, right? You can take their inner product. Let's say I do bra psi ket theta. This is a number, right? Let's say it's some number, I don't know, let's call it A. Well, now imagine that I applied a unitary matrix to these two states, the same unitary matrix. So I have a vector u times ket psi, comma u times ket theta. These are two new vectors. I can also take their inner product. Right, so let's take their inner product. So how do I take the inner product? I have to take the dual of u times psi. So that's going to be bra psi u dagger. Right, so that's just how it works. So like if you take yeah, so this is that's dual of u psi. But notice, here's the thing, u dagger is the same as u inverse. And the u's cancel out. Oops, I think I messed up here. And you get the inner product between psi and theta again, right, as promised. So just think of unitary matrices as just rotations, right? You rotate both vectors in the same way. You're not changing the angle between them. Okay. Before I go on, any questions so far?
I have a question about the unitary matrix. When you do evolution, are you multiplying the unitary matrix by the state of the system before it's collapsed or after it's collapsed?
Good question. So there's no collapse here because the unitary evolution is a separate process than measurement. So when it undergoes this evolution, there's no collapsing, there's no measurement happening. And then there's the separate thing, which is measurement, which then you just measure it and it collapses.
I see. So does that mean that like each time you observe a system, you can only do it like once over the course of like your like observation period or something?
Oh, good question. So I guess for the purposes of like this discussion, we can just think of it as you can just divide up your timeline in terms of there's periods when it undergoes evolution, and then there's periods when you measure it. When you measure it, there's no evolution going on. So after you measure it, it collapses, and then maybe afterwards you say, well, then it'll undergo isolated evolution again. You can say that, but we sort of keep those two things separate.
Okay, got it. Thank you.
Good question. Okay, so I think in the interest of time, I had a couple, actually, I'll just do one quick example, and then there's a few other examples which you can sort of just look at on your own. They should be pretty simple. So here's an illustration. Let's take a single qubit. This is a two-dimensional quantum system. And let's say the qubit starts off in the state ket1. So if I were to draw it as a unit vector in the two-dimensional plane, it's this red vector here. And let's say it undergoes evolution by this unitary. So this unitary is called the X matrix or the X gate. you can sort of check that it's a unitary matrix. And when you apply this unitary x to psi, you're going to get a new quantum state out, and you do the matrix vector multiplication, right? And you'll see that you get this column vector, which is also known as ket 0, right? So what you get out is that's the rotated state. So pictorially, it rotates this state to this state. And there's other gates that are very common. There's this Hadamard gate. You can sort of work through them. But let me come to these Pauli matrices. So these are different unitaries that are very, very important. And they're going to come up in the next lecture for tomography, for example. These are 4 2x2 matrices that have some very, very nice mathematical properties. There's the identity matrix. There's the bit flip gate X that I just described. There's something called the Y gate. Okay, so I here's the square root of -1, and there's something called the phase flip gate. So it's the Z gate. Okay. They're all unitary. They all have these nice properties that I've outlined below. Like if you square each matrix, you get the identity. If you take X, Y, or Z and multiply them with each other, they anti-commute, meaning that, oh, there's a typo here. This should be QP. So PQ is not equal to QP, but instead you pick up a minus sign. All right. They're Hermitian matrices. Maybe I didn't mention what a Hermitian matrix is. Hermitian means, A dagger is equal to A. So if you take its transpose and take its complex conjugate, you get itself back, right? So it's kind of like the complex analog of a symmetric matrix. One really nice thing is that they form a linear basis for 2x2 Hermitian matrices, meaning that if you walk up to me with your favorite Hermitian matrix, that's 2x2, it can be written as some linear combination of I, X, Y, and Z. Okay. And you're going to prove this in the problem set. All right. So let's talk about quantum versus classical bits. Like what's the difference between a quantum bit and a classical bit, right? Like we described quantum bits using these complex unit vectors, but you measure them and there's some weird rule for saying what's the probability you get the outcome. But what's the deal with these like negative and complex amplitudes? Like, does it actually make a difference? So let's consider the following 2 quantum states. The first one is what's called the plus state. It's this equal superposition of 0 and 1. So it's 1 over square root 2 ket 0 plus 1 over square root 2 ket 1. This, you can check that this is a unit vector, right? And it looks like this, right? It's at this 45-degree angle vector. There's also another quantum state, which is called the minus state. And it's the same thing, except there's a minus in between the ket 0 and ket 1. Right? So that's the depiction here. Now, what happens if you take these 2 quantum states and measure them? Right. Okay, so quick quiz, what happens when we measure either of these 2 states, just to make sure everyone's following. Okay, so some questions. I think some people are asking more advanced questions. We're measuring just according to the rules of what I described, you're measuring the standard basis. Good, so you're going to get ket 0 or ket 1 with equal probability for both states, right? Because the minus sign in the minus state doesn't matter because you're taking the absolute value and squaring the amplitude anyways. So it kind of looks like there's no difference between these states, right? But here's the thing: these two states are orthogonal to each other, right? Like if you take their inner product, you sort of compute it, and there's zero overlap between these two states. And in quantum mechanics, whenever you have orthogonal states, that means they're perfectly distinguishable from one another. So that must mean that in order to distinguish the two, we can't just immediately measure them. You have to do something else to them first. Right? So, let's say I had an unknown state. I gave it to you. It's a qubit, and it's either this plus state or this minus state. Like, how could you tell the difference? And the thing is, you don't want to measure it immediately. You want to first apply a unitary to it. Okay, you want to evolve the state first. And the thing to apply is this this unitary, this Hadamard gate, which I didn't go over the example above, but it's a unitary gate. It has this matrix form. And you can think of it, it's a change of basis. So this unitary is going to map these two orthogonal states to the standard basis. So the plus state is going to be mapped by this Hadamard operator to the ket 0 state, and the minus state is going to be mapped to the ket 1 state, right? Like if you do the matrix vector multiplication, you'll see that this is the case. Now, when you measure, you're going to be able to perfectly distinguish between the two states, right? You can identify what psi was originally. Okay, so that's something to keep in mind. Another takeaway that's very important is that this minus sign, at first we said, well, maybe it doesn't matter. Actually, it matters a lot because it's the thing that makes the difference between these two states. And these relative phases, these the signs in between your standard basis states, these matter a lot for whether your quantum states are distinguishable or not. On the other hand, something called the global phase does not matter. Okay, what's a global phase? It's like if you took your quantum state and you just multiplied the entire state by a minus sign, in some sense, there's no, it's not treated as a different quantum state because there's no physical process, there's no unitary, there's no measurements that you can apply that will distinguish between psi and minus psi, right? And that's sort of, that comes from the fact that when you take the absolute value, then like you're applying it, to all basis states, and that sign just sort of disappears. Okay. So relative phases matter, global phases don't. All right. So okay, so for the last part, let's talk about composite quantum systems. And this is where we want to start talking about not just one qubit, but many qubits. And this is where the magic of quantum information starts kicking in, because the dimensionality and the state space is going to grow really quickly. So a qubit is just a unit vector in two-dimensional space, C2. This is called the Hilbert space of a qubit. Okay. It doesn't really matter what a Hilbert space is, but it's the vector space that the qubit lives in. If you have two qubits, the Hilbert space that it lives in is the tensor product space, okay, of C2 tensor C2, right? So the tensor product, hopefully everyone should know what a tensor product is or have heard of it. It's a way of building up larger vector spaces from smaller ones. So if you have, so C2, it has an orthonormal basis consisting of ket 1 and ket 0. And we just combine this basis with itself to form the tensor product space. So C2 tensor C2 is a 4-dimensional space, and it's spanned by these orthonormal vectors 0 tensor 0, 0 tensor 1, 1 tensor 0, 1 tensor 1. And here's the vector representation of these 4 vectors. But actually, as we start taking tensor products, you should really stop, like, not care so much about what the actual vector representation is. We're only going to be working with these like tensor symbols because it's much more convenient. And when we have these tensor vectors, we'll sort of have many different ways of writing them depending on what's convenient. So the longest way to write them is ket I tensor ket j, but oftentimes we'll just drop the tensor symbol. Oftentimes we'll just combine I and j into the same bracket and so on. Okay, so but it should be clear from context what is being talked about. You can think of these 4 basis states as representing the 4 combinations of classical states of the 2 qubits, right? Like each qubit has a classical state 0 or 1. And if you have 2 qubits, you have 4 possible classical states. That's what these tensor states are representing. All right. More generally, so here's kind of like a very important postulate of quantum mechanics, which is like, let's say you have 2 quantum states, maybe 1 particle here, 1 particle there, and you have the description of the state of each particle separately, right? Like maybe one qubit is in the state ket psi and the other qubit is in the state ket phi. How do you describe the state of the 2 qubits jointly? You just tensor their states together. So you get this, this new vector. Okay, this is a vector that lives in the tensor product space. And the tensor product satisfies the same distributive properties, kind of like multiplication. So if we just substitute what psi is, it's alpha 0 plus beta ket 1 tensor gamma 0 plus delta ket 1. Then the tensor product distributes. So we get alpha times gamma 0 tensor 0 plus beta gamma 1 tensor 0 and alpha delta 0 tensor 1 and so forth. So the joint state of these 2 qubits is in this superposition of these 4 classical states with the appropriate amplitudes. Right? So if you were to measure these 2 qubits, you would get the one of these 4 outcomes with appropriate probability. Okay. All right. So I described if you took 2 separate quantum systems, just put them together, you take their tensor product. On the other hand, not every quantum state on those 2 systems can be described in that tensor product form. Right? So a general 2 qubit state, right? It's this unit vector in this C2 tensor C2. It's this linear combination of the 4 basis states. Okay. We know that if you take the absolute values, square them and add them up, you're going to get 1. And a general quantum state, cannot be written as phi tensor theta. If you cannot write it this way, then it's called an entangled quantum state. It means that you cannot give a definitive pure state description to each particle separately. They're entangled, they're correlated. And if you sort of, in some heuristic level, most quantum states are highly entangled. They're not going to be easily factorizable in this tensor product form. Just as some quick examples, there's this important 2 qubit state called the EPR state. It's this equal superposition of either the 2 qubits are in the state 0 or they're in the state 1 they're in the superposition. This is an entangled state. You can, prove to yourself that you cannot write it as psi tensor theta for individual qubit states psi and theta. So you can't separate out the state of these two qubits. On the other hand, you might have this kind of like scary looking superposition if you haven't seen it before, right? It's like, wow, it's like a superposition over these 4 possible possibilities. But you work out the math, you can see that actually this is equal to psi tensor theta, right? So there's no correlations, there's no entanglement between the two qubits. Right. Okay, so let's see. Oh, here we're talking about just some like, how does the Dirac notation gel with the tensor product notation? So basically, this is how you take inner products in this tensor space. You kind of keep the tensor factors together, right? So here's a vector in the here's a bra vector in the tensor space. Here's a ket vector in the tensor space. Take their inner product, and you just take the inner products of these smaller vectors together, right? So you get inner product between A and C times inner product between B and D. That tells you how to take inner products between general vectors in this tensor space, right? So psi and theta, let's say they're arbitrary linear combinations in this tensor space, right? Then you just kind of, right, so this is equal to I comma j. Alpha ij star, you have to take the conjugate. You take the bra vector I comma j. And you sort of just combine everything, right? And you should convince yourself, I'm going through this pretty fast, but if you haven't seen it before, you should convince yourself that this is equal just to the inner product between the alpha ij's and the beta ij's. Okay. And this is a consequence of this like first rule here. All right. Okay, so let's see. Measurement, I think we covered that. Okay, so you're putting these qubits together. Again, you're talking about quantum states on a larger system, and what are the two things that can happen? You can measure them, or you can apply unitaries. You can also build up these unitaries on the larger space from unitaries on the smaller space. So let's say you have U and V, which are single qubit unitaries, like U acts on the left qubit, V acts on the right qubit. And then let's say you apply them separately. From the point of view of the two qubits, the overall unitary is going to be U tensor V. So let's say you have psi and theta here. Well, like I said, the joint state is going to be psi tensor theta. And then if you apply this unitary U tensor V to these two states, U is going to act on psi alone, and V is going to act on theta alone. Okay. Right. And if you really wanted to know what like the matrix representation of this tensor product of these two matrices are, right? Like U and V are 2x2 matrices since they only act on qubits. But if you tensor them together, you're going to get a 4x4 matrix, right? And that's sort of how you compute it. All right. But just like not every state can be factorized as one state tensor another, same thing with unitaries. Not all unitaries have this tensor product form. And if they don't have this form, they're called entangling unitaries, right? These unitaries are going to basically act on both of them both parts together and possibly introduce entanglement between the two. So here's an example called the C0 gate. In the interest of time, like, maybe you've already seen it before, but if you hadn't, you can review this on your own. The C0 gate is sort of like a very important gate in quantum computing. Okay, so here's the final thing that I want to say, or maybe second to last thing. There's this no cloning theorem, which I mentioned. This is a very important difference between classical information and quantum information. Classical information you can always copy. There's nothing preventing you from copying it. Quantum information does not allow you to do that. And formally, how you state this is there's no unitary, there's no physical process that acts on, let's say, a qubit and another qubit. So let's say you're given an unknown qubit psi. You don't know what state it's in, but it's just handed to you. And you say, well, I want 2 copies of psi. So I'm just going to take a second qubit that I'll initialize in the 0 state. And I want my unitary to map psi tensor 0 to psi tensor psi. So you have 2 copies. But there's no unitary that allows you to do this. This is the no cloning theorem. And the proof of this is if there was such a unitary, like it actually wouldn't, it would violate the conditions of being a unitary. In particular, it does not preserve the inner products between vectors, right? So here's a quick proof. Suppose there existed such a unitary that copies psi into psi tensor psi. Well, let's try to copy 2 different states. One state that I'll try to copy is the 0 state. So, well, it's pretty easy to copy the 0 state. It just gives you 0 tensor 0, no surprise. But let's also suppose that it copies the plus state. So if you don't remember, the plus state was this equal superposition of 0 and 1. All right, so yeah, let's say it did that, but this unitary was supposed to preserve inner products. Let's check if that was true. So if you take the inner products of the input states on both sides, let's say we took bra 0 tensor bra 0, inner product with ket 0 tensor, ket plus tensor ket 0. This should be equal to the output states being inner producted together, right? That should hold. But if you do the calculation, you'll get different numbers on both sides. So this is equal to, right? We had this rule for how you take inner products. So this is equal to the inner product between 0 and plus times the inner product between 0 and itself, right? And I claim that this is 1 over root 2 times 1. Right? So this is 1 over root 2. But if you do the calculation on this side, you get inner product between 0 and plus times inner product between 0 and plus. You get 1 over root 2 twice, which is 1/2. Right? Those are different numbers. So that's a contradiction. Right, so very simple proof. If you haven't seen it before, I encourage you to try to run over it again to make sure you understand what's going on. But it's a very important difference between classical information and quantum information that's going to come up essentially in every single thing that we see in this course. So it's super fundamental. Okay, oh, I see there's a question. So Yuval's asking, so what did my proof just show? It shows that there's some state that it does not copy. Is there a stronger result known? Is it possible to construct a unitary that copies almost all states? Good question. So you can improve this proof to say that actually any unitary that copies some states, like you can only do it on like a particular orthonormal basis, and it's going to fail on essentially most other states. Yeah, so it's a very strong impossibility result. Yeah. Okay, so let me end today with this, and this is kind of a little bit of like philosophy for like what makes quantum states so interesting and so different from classical ones. You know, there's the non-cloning theorem that I talked about, but there's also this exponentiality, which makes them very interesting. So we talked about putting, you know, 2 qubits together, you get this 4-dimensional space. But what happens if you put n qubits together, right? Each n qubits by itself has you can describe it using a 2-dimensional vector. But what about all n qubits together? Well, when you take their tensor products, the dimensions multiply. So you get a state space of dimension 2 to the n, which is absolutely ginormous. Each additional qubit doubles the dimensionality of the state space. So in a general n qubit state, psi, you know, you can write it as this superposition over all possible n bit strings, right? And there are exponentially many of them, right? Each n bit string is a distinct classical state, and you can take linear combinations of them. So, you know, these are pretty huge vectors, right? Like if you were to write psi as a vector, like you have alpha 0, 0, all the way to alpha 1, 1, 1, right? This vector is length 2 to the n. It's you know, you won't be able to write it down for any reasonable n. But what's kind of cool is that you have these n qubits, and you apply a unitary, this n qubit unitary to this n qubit state. Mathematically, what's going on? So you have u applied to psi. U is a matrix that it's linear, so you can pull it in, and it's equal to the superposition of u applied to each x. And like if you were to interpret it, it's kind of like saying, like in parallel, I applied u to 2 to the n different classical states all at the same time. At least that's one way of interpreting it, right? And it's sort of like when you look at it, it's like, wow, like if nature's really doing this, it's doing a lot of work behind the scenes. Right, so that's one mystery. And so that's kind of like you think, well, maybe that's where the power of quantum computing comes from, but it's not so simple. It's actually more subtle than that. Like nature is doing this exponential amount of computation behind the scenes, but we as external observers, we don't actually get direct access to this exponential work, this exponential computation. And that's because all this extravagance is hidden behind measurement. Like as you know, we think of ourselves as classical beings, like how do we extract information from a quantum state? We have to measure it. But when you measure, you have this collapse property, and which is really annoying because, you know, you had this vector with 2 to the n different amplitudes. Maybe it had, this amplitudes had really important information you're interested in. But if you measure it, all of that information just disappears and it collapses to like a single deterministic state. So there's this tension, right? There's this exponentiality of quantum states on one hand, but on the other hand, they're extremely fragile, right? Like you do anything to it, like you just look at it, it collapses and you lose all that information. So, you know, this tension makes quantum information really mysterious and subtle. And, you know, we're going to see this come up in this course. Okay, so I think we're right on time. Let me stop here.